Today, we're diving into what's honestly the grandest detective story in the history of human thought, the search for alien life. In this explainer, we're going to go from massive, mind-bending theoretical math all the way down to microscopic grains of ice erupting from hidden alien oceans. We'll figure out why we haven't found anyone yet and how some absolutely wild, cutting-edge evidence is completely changing the game.
I want to hook you immediately with this really stark, kind of chilling question. Because when you look up at the night sky, you're looking at a staggeringly vast universe. I mean, recent surveys say there are at least 2 trillion galaxies out there. 2 trillion. And yet, when we listen to the cosmos, we just get this deafening silence. There are no signals, no massive alien megastructures, definitely no flying saucers landing on the White House lawn. Just silence.
Okay, let's dive right into this. This huge contradiction actually has a name. It's named after the Nobel Prize-winning physicist Enrico Fermi. The story goes that back in 1950, during a totally casual lunch chat at the Los Alamos lab with guys like Edward Teller, they were talking about aliens, and Fermi supposedly just blurted out, "But where is everybody?" That one simple, off-the-cuff question sparked a scientific mystery we've literally been trying to solve ever since.
Part 1. The Cosmic Math.
To really grasp why Fermi's question hit so hard, we kind of have to look at the sheer mathematical probability of alien life. Because if you just run the numbers, the silence of the universe doesn't make any sense at all. Back in 1961, astronomer Frank Drake wrote down an equation. It wasn't really a math problem to be perfectly solved, but more like a roadmap for astrobiology, a list of exactly what we need to figure out to answer this big existential question.
So the crucial point here is the sheer mind-boggling scale we're dealing with. 400 billion. That is the estimated maximum number of stars in our Milky Way galaxy alone. Just our galaxy. That is an almost incomprehensible amount of cosmic real estate.
We can actually break down the key variables of Drake's famous equation pretty neatly. You start with the rate of star formation, right? Then you multiply it by the fraction of those stars that actually have planets. What's absolutely wild is that modern telescope data, especially from the Kepler Space Telescope, suggest there could be as many as 40 billion Earth-sized planets orbiting in the habitable zones of stars just in our galaxy. Think about that. 40 billion chances for life.
Part 2. Where is everybody? So, here is the core contradiction laid bare. If there are tens of billions of habitable Earth-like planets, and many of them are billions of years older than our own solar system, why hasn't anyone come knocking? Even if we assume an alien civilization only has access to relatively slow interstellar travel, the kind of physics we can already envision, the entire Milky Way galaxy could be completely colonized or at least explored by automated probes in just 5 to 50 million years. On a geological scale, that is literally the blink of an eye. Earth should have already been visited, but we have absolutely zero confirmed empirical evidence that it has.
Part 3. The Great Filter Hypothesis.
This brings us to a rather grim twist introduced in 1996 called the Great Filter. It proposes that there is an invisible evolutionary barrier so monumentally difficult to pass, it stops almost all life from ever becoming a spacefaring civilization. We're essentially faced with 2 terrifying possibilities. Option 1, the filter is behind us. This means the leap from non-living chemicals to complex cells is so incredibly rare that we are just a lucky 1 in a trillion miracle. Option 2, the filter is ahead of us. This means life easily evolves to our level all the time, but then almost every technological civilization inevitably destroys itself, maybe through climate change, resource exhaustion, or, mutually assured destruction.
Now, what's really fascinating is a recent 2026 preprint paper by Job Safa Clark. He analyzed the probabilities of these evolutionary hurdles. And he actually argues that no future filter is likely to be destructive enough to wipe out literally every civilization. Instead, he points to a crazy sequence of highly improbable events in Earth's past, like the specific planetary collision that kick-started our plate tectonics. He calculated that the probability of a civilization arising is less than 1 per 10 to the power of 40 stars. But wait, there are only 10 to the power of 30 stars in the entire observable universe. If his math is right, it means the filter is firmly behind us, and Earth might literally host the only technological civilization out there.
Part 4. Searching our solar system.
But hey, science isn't just about sitting around making hypotheses, right? We've got to go out and look.
We're currently hunting for hard, empirical forensic evidence in two primary locations right here in our own cosmic backyard, and they couldn't be more different. On one hand, we have Mars, a dry, dusty world where we're digging through ancient riverbeds for billions of years old fossils. On the other hand, we have Enceladus, one of Saturn's icy moons. And Enceladus is a dynamic, watery world with active ice plumes shooting out from a hidden subsurface ocean right now.
Let's start with Mars. In June 2026, NASA's Perseverance rover made a really stunning detection in an ancient dried-up riverbed called the Jezero Crater. It actually found complex carbon molecules known as macromolecular carbon, or MMC, buried in the mudstone. Now, MMC is a huge building block of fossilized biology here on Earth, but it can also be created by completely non-biological geological stuff. The rover isn't quite equipped to definitively tell the difference yet, which is exactly why these rocks are being prepped for a highly anticipated sample return mission in the 2030s.
And this brilliantly illustrates the contrast with our other big target, Enceladus. In a November 2025 study, researchers revealed some mind-blowing data from the Cassini spacecraft. Get this, Cassini actually flew directly through the erupting plumes of Enceladus, just 13 miles above the surface. It literally tasted fragments smaller than a flu virus and found complex, newly detected organic compounds. And unlike those ancient rocks on Mars, these organics were mere minutes old. They were freshly ejected from the ocean below. This is a potential path to active, ongoing biochemical activity happening in our solar system today.
Part 5. Looking beyond to TRAPPIST-1e.
But you know, our cosmic detective story isn't just local. We are also looking deep into our galactic neighborhood. Our premier tool for this is the James Webb Space Telescope, which has been staring 40 light-years away at an exoplanet called TRAPPIST-1e. It's an Earth-sized world orbiting right in the habitable zone of a red dwarf star. But it is a bizarre place. It's tidally locked, which means one side is in perpetual scorching noon and the other side is in forever freezing darkness. Despite that, it's actually a prime suspect for life, as long as it has an atmosphere that can distribute the heat.
Let's walk through how we actually build a case for habitability from 40 light-years away. Astronomers use JWST to observe starlight filtering through the planet's edges. The dips in that light spectrum tell us exactly what chemicals are there. We've actually just successfully completed Step 2. The latest October 2025 data officially ruled out a thin, primary hydrogen-based atmosphere. So now, the hunt is entirely on for Step 3, finding a heavier secondary atmosphere that built up over time, a lot like Earth's.
Dr. Hannah Wakeford, who's a leading astrophysicist on the JWST team, pointed out something absolutely incredible based on this. She noted that these measurements leave the door wide open for a secondary atmosphere rich in carbon dioxide. This gives us the thrilling, totally real-world possibility that a greenhouse effect could be stabilizing a global ocean right now, or at least a liquid ocean right on that terminator line between the day and night sides of the planet.
And so, here we are at the absolute frontier of what we know. We've journeyed from the staggering, almost unbelievable probabilities of the cosmic math, past the terrifying possibilities of the Great Filter, all the way to microscopic carbon on Mars, fresh organics shooting out of Enceladus, and the atmospheric ghosts of TRAPPIST-1e. But I want to leave you with this one provocative thought to chew on today. If JWST confirms that secondary atmosphere on TRAPPIST-1e, could it be harboring liquid oceans and perhaps actual life at this exact moment? The answers are out there, and for the first time in human history, we finally have the tools to look.